A question that comes up in graph theory is that of shortest networks. In other words, if I were to connect the vertices in each graph shown here, how would I connect that? What would the configuration be so that the length of the edges would be the smallest possible? In real life terms, I might say, how could I connect these nodes with wires so that I used the least amount of wire? And we're going to use that soapy water off to the right in order to help us explore this. Many times we can find answers that we're seeking in the natural world. So we think of graphs as being two-dimensional, just dots and lines, vertices and edges. But in order to use the soap film, I've needed to have these forms constructed where I've got two plates of plexiglass held apart by posts. So we'll start out with our triangular shape. We'll get that in the soapy water. Let it set there for a second. And then pull that out, letting it drip. And look as closely as you can. It may be hard to see. I will be magnifying these later and showing you close-ups, but can you see that there are 3 elements of soap film coming together at this point near the center? So, in other words, 3 edges. So we'll try our rectangle as well. And let's see if we get the same sort of configuration. Are we going to have 3 edges or 3 elements of the soap film coming together? So I'm starting to see a long vertical line there, but near the top and near the bottom, I am seeing points where 3 line segments or 3 edges are coming together, and I'm pointing those out right now. And those actually cut the area around it into 3 equal pieces, which we'll mention later. But let's move on to the pentagon, where we have 5 vertices. Try to get some of the extra bubbles out of there. So here comes that one. See again if you're seeing the same configuration where you see 3 edges coming together at a point in the interior. And we do see that down here. We see it in the middle. Up at the top, it's still there, but the soap bubbles went a little crazy. But we see it down at the bottom, those 3. And we see it in the center. And we're going to take a moment to zoom in a little bit closer. Here are all 3 of our graphs. And then we'll take them one at a time. So here's our triangle. Notice the 3 edges coming together near the center. If we were to go all the way around that center, we would be going full circle, which is 360 degrees. These edges or line segments have cut this up into 3 parts, 3 equal angles. Well, 360 divided by 3 is 120. And what we call that point in the middle is a Steiner point. We move on to our rectangle. Notice again that we have that same configuration where those interior points where the soap film comes together cuts the area around those points into 3 equal parts, giving us 120 degrees each. This is known as a Steiner point. So we'll go ahead and look at our pentagon as well. Again, here 2 of the points are clear. The other one, the bubbles went kind of crazy. That sort of happens when you're dipping in and out of the water. It has been proven mathematically that these Steiner points are needed whenever you're looking for a shortest network. And I just think it's really powerful when we can look at the natural world and take that and also do some mathematical work and put them together and find solutions to our problems or answers to our questions.